things that'll tie in with what Yvonne said. Now, just as a way of introduction, we're going to talk about, again, I'm going to go through some of the slides we did last week or the week before, because I want to emphasize things. And when I do that, I really want you to remember it. That's the thing. Remember, neural crest cells. Some people consider that the fourth layer, embryonic layer of tissue. You know, you've got endo, meso, ectoderm. Well, some people say that neural crest cells, and I would agree with it. I would say that they are. But some people, your text doesn't think so. So it's kind of open. But anyway, they're incredibly important. And the epithelial mesenchymal transformation, EMT, when those little neural crest cells come, here's the trick. They start out as ectoderm. And the neural crest cells, they come off the neural crest, they migrate down, and they go into the mesenchyme, which is normally mesoderm. And what they do then is they take those, what are epithelial cells, and epithelial cells don't move. That's one of their things. They line all of your organs, but they don't move. They're little cuboidal cells that sit on a membrane. Now what happens is those neural crest cells come down, they cause them to delaminate off the membrane, and they turn into mesenchyme. It's kind of magic. It's not magic, it's something that's caused by SOX genes and all sorts of things. But at any rate, then they start moving around the body. Now part of the problem you're going to deal with is if enough of them don't move, or if they don't reach where their target organ is. That's when you have big issues. And so we're going to talk about some of that. But just remember neural crest cells, how important they are. Everything in your life from this point on is neural crest except enamel. And we'll talk about enamel next time. Enamel is ectoderm. But you know what? There's some new evidence that enamel also is influenced by neural crest. Only about 6 months ago somebody came out and said that's the case. I don't know. I don't know. But if that's true, then everything is. But the dentin in the bone, and everything in your face is neural crest. All the muscles, all the soft tissue, all of that. So that's your world from this point on is neural crest. So just do remember that.
What did you say EMT stands for?
EMT is epithelial mesenchymal transformation or transition, whichever one you want to use. That's another thing, is that depending if you're using an embryology text, I don't know if you do, but if you do use an embryology text, you're going to find that some of the words aren't the same as that are in your histology text, the Kate text. So don't be confused by that, but it is that there's a lot of different terms going on. Now I want to ask something. Again, neural crest. How many people in here can wiggle your ears? That's amazing to me. You know, isn't that? It has nothing to do with evolution, other than we don't use them. They're rudimentary little muscles, but that's neural crest too. And those are the facial muscles, and what innervates that? Says the cranial nerve. Do you really think, evolution is all about improving your reproductive fitness? And that just means you have more offspring. The guys, it's all competitive. The animals that have more offspring and the plants that have more offspring win the day. Those of you that can wiggle your ears, do you really think that's going to help you find a mate? Maybe so. Yeah.
Keeps you from dying. You can hear things
I'm not sure that it's a good idea, but there's all kinds of things like that. And that comes from something called pleiotropy, which is when one gene influences all kinds of stuff. Who took genetics in here? Good. Did they have you do, I hope they don't anymore. Did they have you do this? Cross your hands. Now your thumb, if it's on the top, if it's your left thumb or your right thumb, that is genetically programmed. It's true, and it is. And try this. Do it that way. Cross your arms. Which is on the top, your right or your left? I have left. And if you try to go the other way, it just feels creepy. It has nothing to do with anything that's pleiotropy. It's just one gene is selected to do something, and by the way, it happens to change that. And rolling your tongue. Oh, how many people can't roll your tongue? You know this? Well, some people can do what's called a quadrifoil. Can anybody here do a quadrifoil? Good for you. I mean, that's really impressive.
That's
But
definitely
again,
an open.
that's pleiotropy. It has nothing to do with your reproductive fitness. Well, I'm not even going to go there, folks. Okay. Never mind. Okay, just know the words here. Just know that these things are still around and they're bilaterally symmetrical and they have a head end. And just remember, the reason that we have head ends is because that's where first you develop the mouth, and you have to have eyes and nose and ears to figure out where you're going and what you're going to eat and all that kind of thing. So that's an important thing. If you think about what aliens might look like, assuming there are aliens, I think they'd be bilaterally symmetrical? I don't know. Not necessarily. Kind of a spooky idea. I can guarantee you they will not be bipedal. That's the one thing that they always show in the movies, right? The aliens' eyes come down walking on 2 feet. Do you know what the chances of that are? Astronomically small. More likely they're going to be on 6. More likely even yet on 8. But they're sure not going to be on 2 because that's such a weird way to get around. And we're tubes within tubes within tubes. Now, this is trapezius, and the only reason I talk about trapezius is remember, muscles move. It's easy to move a muscle around and have it take on a different function, but in so doing, it drags this nerve supply with it. So this gets a cranial nerve, the spinal accessory nerve, but it's a back muscle. Another one is your diaphragm. You know, anyone here know what innervates your diaphragm? It's funny, it doesn't really matter. But your diaphragm starts out where? In your neck. And then migrates down to where it's supposed to be, where it divides your pulmonary and your abdominal compartments. And humans can't breathe without a diaphragm. If you're a cow, cows can. You can wipe out a cow's diaphragm, it can still breathe. But we can't, standing upright, it kind of screws things up and we can't do it. You know, it's just totally different. It has nothing to do with it. But you might think about it. Women and men breathe differently. Isn't that weird? Because women have ribs that drop down at a steeper angle than men. It's our ribs. Most animals have their ribs come down perpendicular to their spine. And ours drop down. And when you really have to ventilate, if you're out running, what do? You go, and so you pull your ribs up. But women run in a different fashion. They can't ventilate quite as well as men. Folks, it has nothing to do with anything. Other than, that's one of the reasons women are slower. At running, let me emphasize that. Yeah, not the last. Go to the museum and see it. And okay, get into the embryology. Now, here we go, 3 layers. Just remember, ectoderm, mesoderm, endoderm. Originally, you have something called a bilaminar plate, which is just ecto and endo. But then you develop this little cleft down that plate, the primitive streak, and some of the ectoderm goes through the primitive streak and forms the mesoderm. And the mesoderm lines up against the notochord. And these little bumps, and the little bumps are called somites. Now this is going to be important later on, because those somites turn into bone and muscle. And there's a particular area in your head that gets particular muscles that don't come from neural crest cells. We'll get to that. So here we are, ectoderm. There's the mesoderm in between it. There's the endoderm that lines what will eventually be the gut. That's the notochord. The notochord is mesoderm. It's mesenchyme. here you're taking the ectoderm and you're flexing it to form the neural groove, right, over the notochord. And incidentally, the notochord is what triggers all this. The notochord sends transcription factors that go into, that causes the flexion of the ectoderm. It then forms the groove, and it come down here, meets at the top, and it forms the neural tube, which you still have in your body. The neural tube runs all the way from the ventricles in your brain, all the way through your spinal cord. And some of the things he was talking about last week, and that some of the problems that occur on the CNS, the central nervous system, is probably, and this is new too, probably due to the fact that the cilia, essentially all vertebrate cells have cilia. You know, you've seen them. These little like waggy tail things that are flopping around. And what they're mechanical sensors and chemical sensors. If those become disabled, if the cilia on a cell become disabled, you get all kinds of problems. One of the problems you get is spina bifida. Another one is scoliosis, which is lateral curvature in the spine, which is something only humans get. No other animal gets that, except some people tell me whales get it. Now I want to know, how would you know? But maybe they do. I don't know if whales get it. Same thing with menopause. You know that? Some people, humans are the only animals that get menopause. Odd. But some people say whales get it. And again, I say, how in the world would you know? I mean, you're in this ocean. But I guess they know. Anyway, cilia, if they do become disabled, then you get all kinds of problems with hydrocephaly. You get, as I said, spina bifida. You get scoliosis, all kinds of issues. Just another way to show this comes together. And you know, here it's in the neural crest. They call them neural crest cells because they're on top of the neural tube. They're really not there. When they first found them, they found them in chickens, in the embryos of chickens. And then they are on top of the neural tube. In humans, they're slightly lateral, but we still call them neural crests. It doesn't matter. And they go all over. So they come up here, and they start migrating through the body. And they go into the mesenchyme, which is connective embryonic tissue. And they get transformation. One of the things they do is they go into the pharyngeal arches, or the branchial arches. I usually call them pharyngeal because it's in the pharynx. Which, you know what the pharynx is? The pharynx is everything from the back of your oral cavity, your tongue, the very back of your tongue, down to where your brachial, your trachea starts to bifurcate. Just the back of your throat. I show this because this is one of my favorite, this is again a new thing, it's one of my favorite ideas. I didn't come up with it, I wish I had. And then in domestication, what you've actually done is you're selecting for tameness, and when you select for tameness, you're selecting to get rid of things like fear. And how do you get rid of fear? Well, you have to stop the adrenal glands from producing norepinephrine, acetylcholine, and that sort of thing, things that make you nervous. So you have to get that, you have to sort that out. How do you do it? Well, you select for the neural crest not going down to the adrenal glands. Now, isn't that cool? So that in humans, we have very small adrenal glands. So the medulla of our adrenal glands are reduced. Our faces are reduced because it's all neural crest. All these things occur as a consequence of selecting for tameness. And in a social animal like a human, tameness is really what it's all about. Also, we have the most, remember I told you the facial muscles start in the throat, and they move their way up into the face. We have the most expressive faces of all mammals, and that's one of the ways that we communicate. So that's a very important piece too. And you know, and a good example of this, how many times have you emailed somebody, and you didn't mean to sound mean, you were in a hurry, and you just wrote a couple of sentences and you sent it off to them. And they next time you see them, they go, wow, man, what are you upset about? I wasn't upset. And they go, well, your senses made it sound like you're really mean. Because you can't see the face. So much of what we see in people, we read from their faces. So probably facial expression, I told you that sclera in our eyes, we have eyes that you can see the whites of our eyes all the time. That's unusual. So anyway, that's why neurocrest is important. Now, here's a section through an embryo, and you see those little bumps up here? Those are not somites, those are rhombomeres. And those occur in the hind brain, and that's ectoderm. But that's where some of the crest cells come from as they migrate into the pharyngeal arches. Same thing, we took the first pharyngeal arch, remember, there was one, it's now called 0 because it goes up to the nose. And lampreys, it stiffens the nose. But in humans, we take the first branchial arch, and because there's a cartilaginous connection between these two cartilaginous rods, that forms the TMJ, the temporomandibular joint. And that's turns into the maxilla, and it turns into the mandible. And we're about to start talking about facial prominences, or facial processes, or facial swellings, whatever you want to call it, I don't really care. And the facial prominences come about as a consequence of these crest cells moving into the arches. Same thing. And only vertebrates have neural crest cells, which is a major, in evolutionary terms, a major, major breakthrough. We wouldn't be here today if we didn't have neural crest cells. And evolution is incredibly conservative. It doesn't invent new things, or very rarely does it invent new things. Neural crest is the new one. But what it does, it takes stuff you already have and modifies it. It's called a tinkerer. If you tinker with things, you don't come up with new ideas. You just take what you've got and kind of moves things around. Okay. Now, we're starting to see a prominence here. The frontonasal prominence. That would be and you're going to see that some people call it a stomodeum and some call it a stomatodeum. I don't care. It's the same thing. It's the original mouth that starts right in here. There's the first arch. So the first arch buckles in that one place, and you end up here with a maxillary arch and down here with a mandibular. The mandibular is sometimes called Meckel's cartilage. There's the heart expansion, the cardiac bulge is right here, and you start forming things like livers in your guts and all that sort of stuff. Which incidentally, well, we'll see it in a second. So there's the stomatodeum right here. Thing to remember about that is on the outside it is ectoderm, and on the inside is endoderm. There's no mesoderm there, so that whole membrane, the buccopharyngeal membrane, which is also called the oropharyngeal membrane, is bilaminar, made up of ectoderm and endoderm. It then dissolves and goes away, and then the gut has direct communication with the placenta and the uterine fluid. If we section through those arches, and remember they started out as in fish, they turn into gills. In us, they turn into our face. Remember, on the inside, it's endoderm. On the outside, it's ecto, and all the brown stuff in here is mesoderm. Now, on the inside are the pouches. On the outside are either the clefts or the grooves. I don't care which one you call it. People call it different things. Now, there's a laryngeal orifice right there. That will turn into your lungs. So your lungs are made up of endoderm. And so they start at the very back of your pharynx, and then they turn into lungs. So that's what that little hole is. But we're going to talk about these bulges. You see that we've got these little lateral bulges here. Well, those are going to turn into the tongue. And each one of the arches has its own. In the developing heart, there's a vessel that goes above the arches, and that's the dorsal aorta. And the dorsal aorta then branches off and goes into each one of these. So each one of the arches has its own blood supply. It all comes off the dorsal. It also has its own nerve supply. And remember, the nerves stay with the muscles that come out of that. Same old thing. In the Meckel's cartilage does not turn into the mandible directly, but it does form sort of a model for it. But the perichondrium, which we'll talk about later, anything that's chondrium is cartilage. And the perichondrium means the membrane that runs around the cartilage. In bone, it's called periosteum, the membrane that runs around the outside of your bone, which is very highly vascularized and very highly, it has a very strong, incredible nerve complex. If you break a bone, it can be exceedingly painful. Well, that's because it's not the bone that senses it. What it senses it is the periosteum. Perichondrium turns into the incus and the malleolus. And that's why if somebody has a problem in their first branchial arch, if they have a cleft palate, if they have a cleft or a hemimandible, have them look at their ears, have their ears checked, because very likely something's wrong with their inner ear and their hearing. Stapes comes from the second. Remember, stapes used to be part of the reptilian jaw. Well, we stole it, and the reason we didn't steal it, but it migrated into our ear from the jaw joint. Arch 3 turns into the hyoid, which is that bone in your throat. And that just shows you, this all comes off the first arch, so it's the trigeminal nerve. Everything in the face is trigeminal, basically. Not the tongue, we're going to get to the tongue, but most every sensory nerve in your face, and the ones you guys are going to be fighting with Novocaine, is trigeminal. Now I'm going to just bring it, here's a good question, I don't have an answer for it, but I want you guys to think about it. I understand you take a tooth and you coat it in enamel, the hardest thing that biology can make. Enamel has 96% mineral, very, very little organic material. Good. That makes it hard as can be, but that makes it brittle. So you can't make it too thick because you'll crack it if you bite down too hard. Although the sensory feedback from your PDL, which we'll talk about, it doesn't matter. It'll feed back and stop you from cracking your teeth, but you still crack teeth. Now, what you've done is to take dentin, which is like bone, that has a whole lot more collagen in it, a tissue that's compliant, and you put it under the enamel so you don't crack the enamel. Good. It would be a great thing if you could make teeth solid enamel, but you can't because you break them. So you put dentin in there. Okay, good, that makes sense. Now, then you have a pulp inside that tooth, right? You've been learning about teeth. You got the pulp chamber. Inside the pulp chamber is vascularization, good, because you want to keep it alive, and you want to make sure it doesn't dry out. And that's one of the things that happens if you have a root canal, is you get rid of all that, and the tooth will eventually dry out and crack anyway. But doesn't matter. Here's the question: why on earth do you take a tooth, and inside of the tooth you take the most exquisite nerve imaginable and you put it in there? Why? That's crazy. We all know if you have a toothache, that's one of the worst things you can possibly experience. That's awful. Why is the nerve in there? I don't know. Actually, I think I can guess. Because the tooth won't erupt if you don't have a nerve. It'll stay in the crypt. But in that, I mean, what kind of design flaw is that? It just seems to me like, why do you do that? I don't know. Think about it. And that's all trigeminal. Yeah, okay. This stuff you're just going to have to go over. Just know the nerve, by all means know the nerve. Know the primary muscles Know that it's temporalis and masseter and the first arch. Those are your primary chewing muscles. There's a couple other ones, but the big guys are temporalis and masseter. Know that the second one is facial nerve, and that goes to the facial muscles. So your ability to express your face and move it around like no other animal can is due to the facial nerve. That's why people get Bell's palsy, because if you damage it when you're doing, if you have a tumor in your parotid gland, it's often damaged, and you end up with a Bell's palsy. Glossopharyngeal is the third. The reason you want to know about glossopharyngeal is that's hyoid bone. Hyoid turns out is rather complex, it's a little tiny bone, but you need it to talk. And humans have removed, we've taken our pharynx and our larynx, the voice box, and moved it deep in our throat. So we're able to make sounds that, I mean, a chimpanzee can't make the sounds that we make. You can teach them sign language, and they do sort of okay, but they can't make the sounds. It's funny how some birds can make the sounds, though. Fourth arch is vagus nerve. Know that vagus goes all over the body, but you do want to know that the vagus also goes in the very, very back of the tongue, in the epiglottis. Because we've done, and it isn't our fault, but what has happened is, if you look at the gut, if you look at the esophagus, and you look at the trachea, they're right next to each other. The problem is they have to cross each other. And every time you would take a bite of food or take a drink of liquid, you would choke yourself to death. And humans do choke all the time. You know, the whole Heimlich maneuver thing? Well, we choke all the time because it gets caught in there. And it's a very big issue in people that are old, because what happens is the epiglottis that closes off the trachea gets sloppier and sloppier, it just gets old. And then what happens is you aspirate food into your lungs, and then you end up with pneumonia. Another design flaw. It's recurrent branch vagus. Okay, now, just remember, this is cutting through the arches, and the things you got to know. Number one, at the bottom, here's the pouch, the number one pouch. That's the cleft or the groove, it doesn't matter. They come together in this little area, and that forms, what happens out here is you form the ear. That's ectoderm, and the mesoderm forms the auricular pinnae, your ear, which only mammals have. It would be, think about it, if you saw a snake that had ears, that would be very creepy. Really creepy. Well, they don't have ears. Reptiles don't have ears. Only mammals have ears. And external ears. And that comes from that first arch right here. You form the tympanic membrane with the ectoderm and the endoderm coming together to form a membrane, and that's the tympanic membrane, and that forms the eustachian tube, and it also forms the external auditory meatus, which is your ear hole. Come down here, the second arch expands itself, and it obliterates what goes on down here, but it does leave a little hole, and that's the cardiac sinus. There's a little sinus, cervical sinus. That's a little hole in here. It's lined in ectoderm, and that's why you get, he showed pictures of it last time, where you can get those fistula that run down the side of the neck in front of sternocleidomastoid muscle. Then you get the lymphatic tissue, this stuff. You get, you start getting the parathyroid glands, and you get the thymus and the thyroid and all that kind of stuff, which is part of your immune system. Thyroid makes T cells and thyroxine, which allows you to, again, as part of your immune system. The ultimobranchial body forms calcitonin, which allows you to monitor what kind of calcium levels you have in your blood, that sort of thing. These are where you get the fistulas, running down the side of your neck. Also, it can be preauricular up here, so you get those. That's why if you see somebody that's got one, even if they think their hearing is fine, it probably is not. Have them check with that. And you can end up with a a cyst that grows inside. It doesn't go away, or if it breaks through, it's a fistula on the outside. It can also break through internally into the pharynx. Same thing. Sternocleidomastoid is another one of those things that used to be a head, still is partially a head muscle, but it gets spinal accessory nerve. So it also is migrated down the same way that trapezius did. Yeah, we got it. But here I want to talk about the thyroid gland. Thyroid gland, the primordium of it starts up here in the first and second in the endoderm. It then has to migrate through the foramen cecum, down the back of the tongue, down the front of the throat, and ending up down in your neck. Sometimes it gets stuck. It can get stuck in your mouth. It can get stuck somewhere in your neck. It can get stuck around the hyoid bone. Because it's a long way to go, really, if you think about it, for it to migrate down. Normally, it's asymptomatic. But it's, you know, if you see a patient that has a bulge in their neck, or down here, you can also see it down here at the bottom, at the bottom of the top of their throat. You'll often get stuck there. And sort of, that's what it looks like. Okay, the tongue. The tongue, the easiest way to figure out what innervates it is by looking at what makes the tongue. Now, you don't have to do this. If you want to memorize it, that's okay. But I find that it's crazy to try to memorize it. Just think about what makes it. So, here are our branchial arches. Once again, there's that little thing that's going to bulge out and turn into the lungs, the trachea and the lungs. But it doesn't matter. Let's look up here at the first, second arch. You have a median, very early on, a median bulge in the first arch. That is then followed by these two lateral bulges. The second arch comes up with something called a cupula. Do you know what a cupula is? It's an architectural word, or an anatomical. If you have an arch where the two halves of the arch meet at the top, that's a cupula. So that's all it means. It's nothing all that exciting. Now, so the second arch plays a role in the tongue, but it very, very quickly, because what happens is the third arch and the fourth arch grow, meet the first, and they essentially bury the cupula, bury the second. So most of your tongue is made up of the first arch, which, what nerve would that be? Aha! Trigeminal. It's the lingual portion, it doesn't matter. It's the lingual portion of trigeminal, but it's trigeminal, that's all you gotta know. So the tongue is made up of all of this. All of these things come together to form the tongue. I hope I've got a better picture. Yeah, here we go. Same thing. You've got expansions here that start forming the tongue from the first. The second also has that little bulge, but that here they call it a tuberculum impar. Well, that's a cupula. Same thing. It doesn't matter. It's a little expansion in the second arch. Anyway, it doesn't do much. It gets buried by the expanding portions of the third and the fourth that grow forward. Now, here is the tongue as it's essentially fully formed. Now, first of all, there's a median cleft, median fissure that runs down the middle of your tongue. Do you guys do dissections? Are you going to cut through tongues?
Next year or next semester.
Okay, if you take a human tongue and you cut through it, there's a fibrous band that runs up and down the middle of it underneath that fissure. You come back here, and then you see that little line right there? That's the sulcus terminalis. It's kind of a V-shaped thing. If you look at somebody's tongue, you can see it. And the foramen cecum is sitting right there. And that's where the thyroid gland goes. Importantly, what's in pink here that comes from the first arch, that is the oral portion of the tongue. The stuff back here that's made from 3 and 4, that's the pharyngeal portion of the tongue. We know already that the sensory aspect of the frontal 2/3 of the tongue are trigeminal, because that's what forms it. That's easy. We know back here what innervates the tongue, the sensory portion, what innervates the tongue is glossopharyngeal. In the very back, it's vagus, because that's the 4th, and that's the pharyngeal part of the tongue. Those are the sensory inputs into your tongue. Now, here's where it gets kind of messy. That second arch, which is the facial nerve, just didn't disappear. It just got covered over, but it's still in there. So your taste buds on the front of your tongue, which are the papillae, the filiform papillae, that allow you to taste, those are innervated by a portion of the 7th cranial nerve called chorda tympani. It's just a piece of it. It goes through your inner ear down to your tongue. So it's still there, so your taste sensation is chorda tympani, which is 7. The afferent nerve fibers here that allow you to sense your tongue, in the front of it, in the oral portion of it, that's trigeminal. Back here, in the pharyngeal portion of it, that's glossopharyngeal, and that's even vagus. In the very back, which is your epiglottis. Here comes the tricky part. Where do the muscles come from in your tongue?
Mesoderm?
This is an issue, because your tongue is a pretty strong muscle. Some people, I figure it's a lot stronger than others. I'm talking, because they talk, that's what people look like, what's he saying? No. The tongue muscles come from, here we go, they're from muscles that come from the occipital somites. Remember, somites come from the mesoderm. They're those little bumps of muscle. It's called paraaxial somites that run up and down the notochord on either side, and they migrate to your tongue. So they're occipital muscles. Remember, they drag their nerve root with them. So what innervates the muscles of your tongue? Hypoglossal, 12th cranial nerve. So these muscles come forward, and that's what that little arrow here is telling you. They come forward from the back of your skull, and they migrate into your tongue. They drag their nerve system with them, and that is the hypoglossal nerve. So that's the muscles of your tongue. Very important for language.
Can you repeat the chorda tympani function? Is it innervated by nerve from
Excuse me, can you louder, please?
Can you explain again the chorda tympani function and innervation?
Yeah. Chorda tympani is a piece of the 7th cranial nerve. So it's a facial nerve. It's called chorda tympani because it runs through your inner ear. It also plays a role there. It goes into your tongue, and the way to remember that is that you have this second arch is grown over by the 3rd to 4th, but it's still in there. The tissue's still there, and that chorda tympani makes for taste buds.